Alrighty. Thank you all for being here. This is part 2 of the what on earth is the KP index, and how does it relate to the Schumann resonances? Quite honestly, I need the music. I needed that the break at 33 minutes. No, I didn't want to stitch it together and make a bigger one. I like having them at 33 minutes because I can take a drink, have a smoke if I need to, and clear my head on some of this stuff. I'm working at translating some of this into a way that the average person can kind of understand it. And so it takes some work to kind of figure it out and then to be able to translate in some cases. And in some of these instances, I look at the graphs and I'm like, I have no idea what they're saying. And I'm like, oh, I like to look at them. It gives me something good to look at. But it's not that I have no idea, but it's like some have a better idea than others. I'll put it that way. It takes work, for the teacher of the class to put together a lesson. And like I said, I've been learning about much more about the KP index doing these, and I appreciate this opportunity to kind of, I guess, mentor people in what a lot of these topics are, but certainly what the KP index is. All right, so I get part 1. I gave the introduction. Part 2 here, the first part of the magnetometers, I read through what the KP index is. It's logarithmical. I'm not going through any of that again. I've had enough of that. So the magnetometer, what is the magnetometer itself? What's the measuring device? All right. And that is what is of interest to me here in this particular video. My stated clear intention, what am I looking to talk about? It's the magnetometers themselves. Boom. So this is one of those ones that a lot is given, a good deal is given. All right, so the best source of no, hello, please don't do that again. All right, so the best source on a lot of the stuff, first place to look that I check out, it's Wikipedia, and they're giving me a good working definition in a lot of cases. Then what I do is I go down to the references in the bottom and I start flipping through stuff they give me, and then that's how I came across the letter from Gauss, which in itself is interesting. All right, so I'll read through what it says here. A magnetometer is a device that measures magnetism, the direction, strength, and relative charge of a magnetic field at a particular location. The measurement of the magnetization of the magnetic material, like a ferromagnet, is an example. A compass is one such device, one that measures the direction of an ambient magnetic field, in this case, the Earth's magnetic field. All right, so scroll over. What does it say for magnetism? Magnetism is a class of physical phenomena that are mediated by magnetic fields. Electric currents and the magnetic moments of elementary particles give rise to a magnetic field, which acts on other currents and magnetic moments. Magnetism is one aspect of the combined phenomena of electromagnetism. All right, so there's more to that. Okay, a magnetic field is a vector field that describes the magnetic influence on moving electric charges, electric currents, and magnetized materials. A charge that is moving in a magnetic field experiences a force perpendicular to its own velocity and to the magnetic field. Right. This is showing you magnetization. It's a class of electromagnetism. Magnetization or magnetic polarization is the vector field that expresses the density of permanent or induced magnetic dipole moments in a magnetic material. The origin of the magnetic moments responsible for magnetization can be either microscope or I'm not going to click on that. All right. Ferromagnet is the basic magnetism by which certain materials form magnetic permanent magnets or are attracted to magnetics in physics. Several different types of magnetism are distinguished. Ferromagnetism is the strongest type and is responsible for the ferro is iron. Right. So an iron magnet. They turn a piece of iron into a magnet. Right. Compass. All right. Compass is an instrument used for navigation and orientation that shows that shows direction relative to the geomagnetic cardinal directions. Usually a diagram called a compass rose shows the directions north, south, east, and west on the compass face as abbreviated initials. All right. I can remember. All right. So the first, all right, back to our text. The first magnetometer capable of measuring the absolute magnetic intensity was invented by Carl Friedrich Gauss in 1833. A notable developments in the 19th century included the Hall effect, which is still widely used. What does it say about the Hall effect? All right. The Hall effect is the production of voltage difference across an electric conductor, transverse to an electric current in the conductor, and to an applied magnetic field perpendicular to the current. It was discovered by Edwin Hall in 1879. For clarity, the original effect is sometimes blah, blah, blah. I'm not going into that. All right, that is the Hall effect. Okay. Where are we at? Magnetometers are widely used for measuring the Earth's magnetic field and in geophysical surveys to detect magnetic anomaly of various types. What does it say, magnetic anomaly? And what it says of magnetic anomaly is a local variation in the Earth's magnetic field resulting from variations in the chemistry or magnetism of the rocks. Mapping of variation over an area is valuable in detecting structures obscured by overlying material. The magnetic variation. All right, so we're going to. Magnetic anomalies of various types in aircraft's attitude and heading reference system. They're commonly used as a heading reference. Magnetometers are also used in the military to detect submarines. Consequently, some countries, such as the United States, Canada, and Australia, classify the more sensitive magnetometers as military technology and control their distribution. Well, that's interesting. Magnetometers can be used as metal detectors. They can detect only magnetic ferrous materials, but can detect such metals as a larger materials at a much larger depth than conventional material detectors. They are capable of detecting large objects such as cars at tens of meters, while a metal detector's range is barely more than 2 meters. In recent years, magnetometers have been miniaturized to the extent that they can be incorporated in integrated circuits at very low cost and are finding increasing use as miniaturized compasses, MEMS magnetic field sensors. All right. So they're using magnetometers on integrated circuits as a form of a miniaturized compass. Okay, this is fascinating. All right. I just want to say, thank goodness I only have to go through this once. You know, even though I'm a technical-minded person, some of the technical and the scientific reading that I got to do for the Schumann and for, you know, a program like this, show like this, it's like I admit that it is kind of beyond me in some cases. I just want to be one with everyone else and saying, well, God, this is kind of complicated. And yeah, it kind of is complicated. So that's why I do my best to work to get this stuff so it's understandable to the average person. And I'm working to make this accessible to myself as an otherwise simpleton, and to the average people, the average person. And so that's why I appreciate getting comments from people on these subjects, because I want to know how I'm doing and giving this out to you so it's understandable. And so I just want to make that clear, for what it's worth. All right. So what we're looking at is types of magnetic fields. All right. I'm not going to have a little music in the background because this is just to kind of spice things up for me. All right, so in introduction, magnetic fields. Magnetic fields are vector quantities characterized by strength and direction. The strength of a magnetic field is based in units of Tesla in the SI units. I don't know that before. Tesla. I wanted to have that as a open link in another. All right, whatever. Okay. Yep. And in Gauss. All right. So the strength of the magnetic field is measured in units of Tesla in the SI scientific notification units, and in Gauss in the CGS system of units. 10,000 Gauss are equal to 1 Tesla. Measurements of the Earth's magnetic field are often quoted in units of nanotesla, NT, also called a gamma. The Earth's magnetic field can vary from 20,000 to 80,000 nanotesla, depending on location. Fluctuations in the Earth's magnetic field are on the order of 100 nanotesla, and magnetic field variations due to magnetic anomalies can be in the picotesla range. All right, so this right here, the picotesla, is the range of the Schumann resonance harmonics. Gauss meters and Tesla meters are magnetometers that measure in units of Gauss or Tesla, respectively. In some contexts, magnetometer is the term used for an instrument that measures fields of less than 1 millitesla, MT, and the Gauss meter is used for those measurements greater than 1 millitesla. Types of magnetometers. There are 2 basic types of magnetometers measured. Vector magnetometers measure the vector components of a magnetic field. Total field magnetometers or scalar magnetometers measure the magnitude of the vector magnetic field. Magnetometers used to study the Earth's magnetic field may express the vector components of the field in terms of declination, which is the angle between the horizontal component of the field vector and the magnetic north, and the inclination, which is the angle between the field vector and the horizontal surface. Okay. I am moving myself to I can get a better angle on this. All right, here we go. Absolute magnetometers measure the absolute magnitude or vector magnetic field using an internal calibration or known physical constraints of the magnetic sensors. Relative magnetometers measure magnitude or vector magnetic field relative to a fixed but uncalibrated baseline, also called variometers. Relative magnetometers are used to measure variation in magnetic field. Magnetometers may also be classified by their situation or intended use. Stationary magnetometers are installed in a fixed position and measurements are taken while the magnetometer is stationary. Portable or mobile magnetometers are meant to be used while in motion and may be manually carried or transported in a moving vehicle. Laboratory magnetometers are used to measure the magnetic field of materials placed within them and are typically stationary. Survey magnetometers are used to measure magnetic fields in geomagnetic surveys. They may be fixed base stations, as in the intermagnet network, or mobile magnetometers used to scan a geophysical region. Okay. I don't know. Performance capabilities. The performance and capability of magnetometers are described through their technical specifications. Major specifications include, I think this is important to read, actually. Sample rate. Yeah, this is a great thing. Sample rate is the amount of readings given per second. The inverse is the cycle time in seconds per reading. Sample rate is important in mobile magnetometers. The sample rate and the vehicle speed determine the distance between measurements. Okay. The next one is bandwidth or bandpass characterizes how well a magnetometer tracks rapid changes in magnetic field. For magnetometers with no onboard signal processing, bandwidth is determined by the Nyquist limit set by sample rate. Modern magnetometers may perform smoothing or averaging over sequential samples, achieving a lower noise in exchange for lower bandwidth. All right, so this is something that happens with the Schumann as well. Resolution is the smallest change in the magnetic field the magnetometer can resolve. A magnetometer should have a resolution a good deal smaller than the smallest change one wishes to observe. Quantization error is caused by recording round-off and truncation of digital expressions in the data. Absolute error is the difference between the readings of a magnetometer true magnetic field. Drift is the change in absolute error over time. Thermal stability is the dependence of the measurement on temperature. It is given as a temperature coefficient in units of nanotesla per degree Celsius. Noise is the random fluctuations generated by the magnetometer sensor or electronics. Noise is given in units of nanotesla over the square root of hertz, where frequency component refers to the bandwidth. All right, so the frequency component is here, hertz, the square root of a hertz. Sensitivity is the larger of the noise of the resolution. Heading error is the change in the measurement due to change in orientation of the instrument in a constant magnetic field. The dead zone is the angular region of magnetometer orientation in which the instrument produces poor or no measurements. All optically pumped proton-free precession and Overhausen magnetometers experience some dead zone effects. Gradient tolerance, last on the list, is the ability of the magnetometer to obtain a reliable measurement in the presence of a magnetic field gradient in surveys of unexploded ordnance or landfills. Oh, gradients can be large. Oh, that's interesting. That's interesting. So early magnetometers. This was one of the things that I had posted on I posted a picture way over here of an older, hello, I don't like when I do that, thank you. I had posted that of an older magnetometer. Alright, so there's a number of magnetometers that are here. Alright, I'm scrolling through this really quickly because I'm not going to, I'm at 23 minutes. I don't want to make a whole nother video on just this one thing. But you can see mineral exploration, mobile phones, oil exploration, spacecraft, magnetic surveys, magnetovision, heading errors in magnetic surveys. Alright, and then they give the references. Alright. So, there's a lot more here. This was, and again, it's the topic of this is magnetometers, but this is really an introduction to what the magnetometer is, what it does, the different types. And you have, and I just want to say, this one here, the inductive pickup coil. Oh, crap. Sorry about that. The induction pickup coil is that right there. Right. So this is the magnetic induction coil. All right, and this is our Schumann magnetic induction coil. It says magnetic induction antenna. Our magnetic field antenna consists of two individual back-to-back induction coils with mu metal core metal material in order to achieve core alignment and excellent connection between the two induction coils, blase, blase. All right, so that is the magnetic induction coil. All right, I just want to make mention of that. All right, so it's a little music to clear the brain cells. All right, so I'm gonna do this once. We'll never have to do it again. There's laboratory magnetometers. That's this great one here, showing you from way back when, probably from Gauss himself. Squid, there's a superconducting quantum interface device. Squids are a type of magnetometer used both as survey and as laboratory magnetometers. Squid magnetometry is an extremely sensitive absolute magnetometry technique. However, squids are noise sensitive, making them impractical as laboratory magnetometers and high DC magnetic fields, and impulsed magnets. Commercial squid magnetometers are available for temperatures between 300 millikelvin, I guess, and 400 kelvins. Magnetic fields up to 10 Tesla, or I'm sorry, 7, it just says. The induction pickup coils, also referred to induction center, measures the magnetism by detecting the current induced in a coil because of changing magnetic moment of the sample. The sample's magnetism can be changed by applying a small AC magnetic field or rapidly changing DC field, as occurs in capacitor-driven pulse magnets. These measurements require differentiating between the magnetic field produced by the sample and that from the external applied field. Often a special arrangement of cancellation coils is used. For example, half of the pickup coil is wound in one direction and the other half is in the other direction, and the sample is placed in only one half. The external uniform magnetic field is detected by both halves of the coil, and since they are counter-wound, the external field produces no net signal. All right, so that's interesting. All right. So I'm not going to get into, I'm just going to kind of read these up, but I'm not going to get into the descriptions. You have the VSM, which is vibrating sample magnetometer, pulsed field extraction magnetometer, torque magnetometry, Faraday force magnetometry, optical magnetometry, survey magnetometers, scalar. So there's a number of types of magnetometers that are used out there for all kinds of. There's one, potassium vapor magnetometer, vector magnetometer, rotating a coil, Hall effect magnetometer. Okay, so with that read in that scene, okay, I introduced the magnetometers. There's one more thing I wanted to get back to, and that is this here. All right, so I have roughly 4 minutes left of this. Okay, I'm back. All right, I got like 4 minutes or less to explain, 3 minutes I'm at, to explain, this is 30 pages, I'm not going through all this, but this is written by Carl Friedrich Gauss. He's the one that they give the credit to, the father of the magnetometer. All right, so there we go. Lovely. All right. So I'll just read you the kind of the introduction, what it says. The intensity of the Earth's magnetic force reduced to absolute measurement by Carl Friedrich Gauss. The intensity of the Earth's magnetic force. This is from the treatise Intensitas vis magneticae terrastris menstruum, by Gauss and the Guttengeller Gesellschaft der Wissenschaft, the Royal Scientific Society. All right. I haven't even get into the article yet. All right. So it says, for the complete determination of the Earth's magnetic force at a given location, 3 elements are necessary: the deviation or declination, or the angle between the planes in which it acts, and the meridian plane, the inclination of the direction of the horizontal plane. Finally, third, the strength or intensity. The declination, which is to be considered as the most important element in all applications to navigation and geodesy, has engaged astronomers and physicists, from the beginning, who for a century have given their constant attention to the inclination as well. In contrast, the third element, the intensity of the terrestrial magnetic force, which is surely just as worthy a subject of science, remained fully neglected until more recent times. Humboldt rendered the service, among so many others, of having been first to direct his attention to the subject, and in his travels assembled a large array of determinations concerning the relative strength of magnetism, which yielded the result of a continuous increase in the strength from the magnetic equator toward the pole. A great many physicists have trod in the footsteps of that great natural scientist and have already brought together such a large array of determinations that hand